recently I just learned about Fourier series and Fourier transformation. So if you are a beginner in this thing, just check out 3 Blue 1 Brown's playlist on this, and then check the Wikipedia page. This will make much more sense when you read the Wikipedia page. Right. So what is this video about? Am I going to teach you in detail what Fourier series actually is, how it behaves, why do we use it? No, I won't be doing that. You can have better sources than me for doing it. First of all, uh, the first thing that I want to say is that Fourier series, it's mostly used to basically imitate periodic functions using sine and cosine waves. And really, it's better to just use complex exponentials because they are easier to handle, but actually it should be sine and cosine based if we are just dealing with a real valued function. Right, and for this particular example, we want to deal with the function fx is equal to x square in negative pi to pi, but then this function repeats itself. So the actual graph of this function, it's like this. So x minus 2 pi, floor of x plus pi upon 2 pi. So x plus pi, it just shifts basically pi backwards, and that's required so that you actually have from here to here, whatever the thing is, you just make that thing periodic, and then that upon 2 pi to scale it down so that we can apply the floor function, and then that times 2 pi to scale it back up, right? Yes, the floor function is the thing that makes it periodic, right? Yes. Yeah, so that's this graph, the red graph. So I'll just disable this thing so you can see it better. So this is how it looks, right? So you can see it resembles f of x equal to x squared in this region, negative pi to pi, but then it's just this thing copied over here as well, and yeah, it keeps on going. Right, so that's good. And now let's enable this graph. What is this thing? So you can read all of this, and you can see I arrive at this final approximation, or I should say approximation. It is in fact the same thing as f of x. So this is our Fourier series for f of x. So let's go through it. First thing we do is assume f of x is of some particular form. So my assumption is that it's the sum as n goes from negative infinity to infinity of c sub n e power I n x. So why I n x? Because it has period 2 pi. So the period of f of x should be 2 pi, right? And that's why I have this thing. So n is just an integer, right? And that's why it does have the fundamental period as 2 pi for all of these exponentials, right? And cn is just some complex constant. You don't have to worry about that all that much till now, right? For this definition, the constant could be anything, right? But we are just assuming that it is of this form, and then we'll try to figure out what these constants are, and we'll actually graph this. So you can see this thing is the graph, how it should be, right? So let's start. How do we do this? First of all, we'll multiply by e power negative I kx, and then we'll integrate over one period of this thing. So what do I mean when I say one period? So it's from negative pi to pi. Whatever is happening, the same thing happens when you repeat this, right? So that's one period of this function f of x. So you will integrate over that. So we are integrating from negative pi to pi of f of x e power negative I kx, right? And you look at this sum, n minus k is going to be not 0 and some integer whenever n is not equal to k. So for only the n equal to k term, so basically c sub k e power I kx, for that term, when you multiply it by e power negative kx, that will just be a constant term. So that guy's integration, that will be 2 pi ck, but everything else will just be 0 because it's basically you are going yeah, so the other things will just be 0 because you're just adding up a lot of vectors in symmetry, so it just goes to 0. That I don't have to explain. right? And yes, that integration is not a counter integral. Instead, it's just integration over real values of x, right? So negative pi to pi. So don't get afraid that something, I mean, complicated is happening in there. It's just normal integration. So yes, and then once we have this equation, you can write ck as 1 upon 2 pi times this integral. So f of x in negative pi to pi, we already said it should be x square, and that's why negative pi to pi x square e power negative I k x dx. Now do this using integration by parts, and you will get this value to be 2 upon k squared negative 1 power k, and be extra careful because it's negative 1 power k, this factor, this does happen over here. At first I didn't actually catch that, and yeah, I got a different series and I thought that was pi squared upon 12, but no, actually the net says it's not. That series that I got, that was just 1 upon n squared plus 1. So like the sum of 1 upon n squared from 1 to infinity, that is not pi squared upon 12, that's pi squared upon 6, right? So if you ignore this negative 1 power k, you will get a wrong result. So yes, that's there. And next what we do is that we just combine two terms from the summation. So it's going from negative infinity to infinity. So you will have all the negative values of n along with their corresponding positive values of n. So you can combine those two terms. Oh, it should be positive, right? So this thing, it should be the sum over here. And I wrote it as, okay, just wait a second. Right, so this thing, it should be the sum, not the difference, of course, because it's in the summation. It's not supposed to be the difference anyway. So we got that, huh? All right. Okay, let's go back to full screen. Yes, or in fact, let's just skip that, not go back to full screen. Okay, so this sum using Euler's theorem, you can write this thing like that. Okay, and of course this doesn't work for k equal to 0 because this will give us something not defined. So for c0 we have to do that individually. So it's very easy. In fact, just integrate it directly, just negative pi to pi, and everything else has the complex exponential with it, so it adds up to 0 in the integration, but this constant thing, it doesn't, right? So it's c0 times 2 pi is equal to the integration of f of x from negative pi to pi, and f of x is just x squared in that range. So it's just x cube upon 3 from negative pi to pi, and then doing everything, just get pi squared upon 3 as c0. So you can finally write what f of x should be. So notice I have 1 to infinity now in this summation. That's because you already took care of the negative n values when you combine these two terms to get one single term, right? So you already you have taken care of the negative ones, right? And that's why we can directly write this as 1 to infinity. And I'm not including 0 because that's also over here. We don't need to do that. So that's it. We got f of x as an infinite sum of these sine cosine waves, right? And then there's this yeah, and the functions of n and whatever. Cool. So here's a nice graph for this thing, for this function. So this is being approximated right now. It's not going till infinity because, of course, and it's only going till m. As you can see in this thing, this is going till m. So as m increases, your approximation becomes the reality. So you will see what I mean by that. So m is equal to 0, it's a straight line. Then m equal to 1, it's something like this. So it's a straight line plus some plus an cosine curve, and it does look like a cosine curve. And then you increase it once again. So yeah, now it doesn't look all that much like cosine curve because you have this kind of weird I don't know what this is. It's not very much like a peak. It's a less steep peak, or wait, it's not a peak actually. It's like a valley. Whatever, you get the thing, right? It's not looking like cosine at all now. And then we keep on going, and you see it resembles this red curve more and more, and then 4, 5, 6, and so on. And then when m becomes really large, you see it actually becomes the curve itself. So Yeah, from here the difference is just indistinguishable. So sorry, it's not noticeable. But when you zoom in really hard, you see that these two curves are actually not yet the same. So you can just keep going, and yeah, this will become same, right? So I will go till 20. At this point, these would be very much the same thing, except for these small triangular regions over here, right? So why do we care? We care because this can give us some really nice things. So when you put x equal to 0 into this equation, right? The expression for f of x, when you put x equal to 0 into that expression, you get this infinite series. So it's basically like 1 upon n square, 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square, so on till infinity. That thing is pi squared upon 12. And from this, you can figure out what 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square, so on till infinity should be. And that's just pi squared upon 6, right? So that's all I wanted to say. See you guys in the next video.